Uh, these, some of these.
It's the W.
Yeah, this is the one we want. Okay, some of these you're getting, you will not have seen all of these, but you might. I mean, there's a whole plethora of problems that you can see on this test. It's very random. Okay, but if we're given this function and we want to pick its derivative, we haven't talked about that in a little bit. What are going to be? What are going to be some? We'll sketch the derivative on top of the function. How about? How are we going to do that? We want to look for some anchor points. Are there some points where we know what the value of the derivative has to be?
0.
0. Yeah. Okay, we're going to look for all the places. Those are the ones that we know for sure. The other ones are just kind of estimates. We don't really know, for example, and we're not going to take the time to actually calculate how steep the graph is there numerically. We just know that it's negative and big, right? But there are a few places where we know exactly the value of the derivative, namely the places where we have horizontal tangents and therefore 0 slope, right? So we know that in those 3 places we would have to have our derivative function. We have to have 0 values, so those would be x-intercepts. And from there, all we're really doing is we're just trying to determine, surrounding those zeros, is it positive or negative, right? So let's just do something like this. How about if we just make some, we're just going to divide this thing up into regions, right? What about over here? To the left of this 0, is it positive or negative? It's negative, right? It's very negative, and then it's less and less negative, eventually goes to 0, right? So our function's going to look something like, that then, isn't it?
Yeah.
Right? Okay, what about in here, between there and there? It's going to be positive. It starts off small, it gets very positive, and then it diminishes back to 0. So doesn't that mean it's going to do something like, hang on a second here, I got to maybe redraw. I don't like this one. It's got to go something like that, right? I mean, you get the idea. I probably didn't draw that very well, right? But you get the idea? And then down here, it's 0. It gets very negative right here, right? Then it goes back to 0. So it's doing something like that. And then it gets increasingly positive. So that's the basic shape. You get the idea, right? And you kind of want to just think about, you could even draw little tangent lines on there to kind of, so that's very negative, less negative, right? Okay, so which one is it? Well,
B. It was B.
so it's definitely B, yeah. Okay, makes sense? Oh, yeah. Any questions on that? So find the zeros, and then you just want to kind of find the nature of the derivative between the zeros. Is it positive or negative? Is it, draw the little tangent lines in. This is a big, these kind of really aren't very hard, but you see a ton of these, like for example on the advanced math tests, AP tests, SAT tests, AP specialty tests, stuff like that. These are real popular ones.
So, like, what if it had, like, that, okay, so that's our answer.
Mhm.
What if it showed you that and you should find the derivative?
Of this? Okay, well, let's look at that one. Okay, what if, let's take another practice. Let's say pretend that's the original function. Okay, so how many zeros are there on this one?
2.
2. Okay, so we're going to get zeros. Whoops. We get zeros. There's a horizontal tangent. There's a horizontal tangent, right? So we get a 0 there and a 0 there, right? If we split this thing up now, to the left of this 0, how would you describe the behavior?
Positive.
Okay, and is it going from left to right? Is it getting more or less positive?
More.
The slope.
Less.
Less because it's flattening out and going to 0, right? So that means it's doing something like, whoops, you get the idea. It's doing something like this then, isn't it? Right? And then between here and here, starts off at 0, it gets, pretty negative at that point, and then it backs off and goes back to 0. So something like that. It's out of scale, I'm sure. And then on this side, it starts at 0 and it just gets increasingly positive, so that's our picture,
Okay,
okay?
thank you.
Does that make sense?
Yeah.
You can notice some trends here too, and you know, we'll talk more about this. Next chapter, we're gonna do a lot of functional analysis and curve sketching. That's really what the next unit's all about. But you do notice that the complexity of the polynomial goes down, which makes sense, doesn't it? When you differentiate a polynomial, you get a 1 degree smaller polynomial, right? And so in this case, we went from a cubic to a quadratic, right? The number of zeros decreased by 1. I mean, this one, it wouldn't necessarily even have to, right? I mean, this thing could be lifted up, or that could have been down here without any actual zeros. But I guess a better way to look at it is the number of turning points, right? The number of turning points went from 2 to 1. And you might remember going back to, you know, to like honors algebra 2 and pre-calculus talking about polynomials. Remember that if it's an nth degree polynomial, so say it's a 3rd degree polynomial, what's the most turning points you could have?
3, 2.
2, n minus 1, right? So this would be a classical cubic, right? This is a classical quadratic. Now, it could be that the cubic does this. You know, it might do something like this where it only has, you know what I mean? It might not have those 2 turning points, but it could have up to 2 turning points, okay?
How do you get like the horizontal line on for A?
Okay, now that's the answer. You tell me what kind of, so if this is gonna be the actual derivative of the function, what would the function have to be that would produce that derivative? There you go, yeah, good, something like this would it be just a line with a constant positive slope. Okay, does that make sense? Okay.
That's what I thought.
All right, so moving on here. Yeah, it's small, we make that a little bigger. Is that something you wanna, I mean,
Might as well. Might as well.
So we're supposed to find DYDX. Okay, what about this guy? So, you know, once again, on these, don't worry about that, you know, just ignore that. You don't even have to have that. They're trying to give you some additional information, help you out on this, but I think maybe it just was confusing to some people. So just ignore it. It doesn't even need to be there. Forget that one, okay? So if we're gonna differentiate this, I mean, this is just chain rule stuff, right? So how many layers?
2.
2. All right, so then y prime equals, what's the first layer?
Cosine hand.
Cosine, good. So derivative of cosine hand is?
Negative sine hand.
Jeez. Times. And remember now, in this, you're getting much better at this, but I still saw as I'm going through the tests and kind of looking for partial credit and seeing what you did, there still was a tendency sometimes, I think just when you know, maybe when you're just kind of getting confused on something, to mix up those links. The links have to be separate. So sometimes people wanted to do things like, well, this is maybe a bad example. But I think this is a bad example. When we get to one where it'll make more sense, I'll show you how that happened a little bit. What would the next layer be then if I peel away the cosine? 4, good. So we would just make that -4 sine of the quantity 4x plus 9.
That is correct.
Okay. Okay, this is a good one. This is one I definitely want to do. This was a
Wait.
this one didn't. I was looking at the stats on the test, and this one was not highly successful as a group. So let's.
I didn't get this one. I didn't get this one. I didn't get this problem.
Okay, so and this is kind of a bad one. I mean, it's how many layers to this?
7.
7.
1, 2, 3.
It's, I guess you could say 3. It's a on the outside level. It's a power
Yeah.
2, and on the inside it's a
Quotient.
quotient, yeah, dreaded quotient, okay.
Oh, I didn't see that. Are you guys
That's dirty.
So first things first, okay, and here's maybe an example, like when people mixed up the steps, what people might have tried to do on this, in some cases, is bring down the 2 and then multiply 2 times the quotient rule. So not actually separating the links in the chain, right? So remember, the first link is, we don't even care what's in there. The derivative of hand squared is
Two hand.
2 hand. We haven't even looked what's in there yet, right? We just know that the outer level, it's a power. So 2 times something to the 1. We haven't even looked in there. Okay, well, it's sine x times 1 plus cosine x. Remember, you only differentiate once per link, right? Times
Quotient rule.
the derivative of what's inside, well, that's a quotient. So yeah, we're gonna have to make a big quantity there to do, right? Set up some brackets to do the whole quotient rule.
92.
So what's quotient rule tell us here?
1 plus cosine x?
1
V x squared.
Times cosine x.
times derivative of sine is cosine, good.
He's on a roll.
Minus sine x. Times
Negative sine
x.
x.
Times negative sine x.
Okay.
Good, just derivative of cosine, good, makes sense? Questions on that? Okay, divided by,
1 plus cosine x squared.
That's dirty.
good, the quantity 1 plus cosine x squared, good. So what's next?
You do it all.
Yeah, we gotta clean up that top, don't we? So if we distribute the cosine, this is gonna give us 2 sine x, and then we're just gonna put everything on the top that's on the top, everything on the bottom that's on the bottom. But this whole thing right here, what's that gonna be? Well, if I distribute the cosine, I just get cosine x plus cosine squared x.
Yes.
Okay. Now what about this over here?
Plus sine x squared.
Wait a second, where'd you get the, why is it just cosine by itself?
Because we did this.
Multiply by
Because we
one.
took this cosine and we distributed it.
Oh, okay.
Okay, make sense?
Okay.
It's over that
Why do
cube.
you take
Okay,
both?
good. And there's the kind of another key on this one is knowing is seeing that trig identity. We haven't done a ton of real complicated trig identities, but this is one that pops up a lot, right? Pythagorean rule for trig
It
functions.
is one.
So this, right, this whole thing is 1. Okay? Divided by, now what's on the bottom? Let's see, we got a 1 plus cosine x times a 1 plus cosine x squared.
Cubed.
Good, 1 plus cosine x cubed.
Kill him.
And,
Or could you just,
exactly, well, you we're gonna be able to, aren't we? Because look, now when this goes to a 1, I'm gonna write this step down, but you see where this is going.
yeah.
All this stuff just becomes 1 plus cosine x. Okay, everybody see that?
Mm-hmm. It does.
And then we can just cancel one of those, right? And we're done.
It's 2 sin x.
He doesn't make sense.
Yep, quantity squared. Make sense?
I feel like I get this one.
Okay. So separate those links in the chain.
Yeah.
All right, next. This one, I want to do this one too.
I like
I know we've done a lot of these, but I just, there were enough people still had trouble with that.
Sure.
Plus x plus t equals the square root of pi.
Oh, I know that one.
Those ones are horrible.
Okay, so something like that. Outermost level, what pattern or what rule do we use? Product rule, yeah. We got a product of, did everybody see that? We have a product of the green factor and the red
Oh, Christmas colors.
factor. Yeah, notice that?
Christmas.
All right, so,
You see it's
okay, so product
That's
rule.
true too.
Product rule. What are we gonna give for product rule here?
X.
Okay, so we got,
You have to do a chain roll for 2x minus 1.
you're right, yeah. So we got x cubed times the derivative of the red stuff, right?
Oh, geez.
Dirty.
So
That's
that's
right, that's gonna be,
times the quality.
so that derivative is chain rule. Yeah, we got outside, we got hand to the fourth,
Two. Yeah.
right?
Times 2.
And then the derivative of what's inside, if we peel that away, is 2, sure.
Plus.
So, okay, so there's first times derivative of the second. Now we gotta do plus second
Right, yeah.
times derivative of the first. Good. Okay. And we can, okay, and so now, here's another thing that even though the test would have marked you as having 0 if you just kind of left this as 2 terms, cleaned it up and left it as 2 terms. I did go back, and I'm still in the process of going back. I'd give you some partial credit for doing the calculus part right. You're not gonna get a ton, but I'll give you some for that, so that, your scores will be improving a little bit on these tests, but still, I think most people are gonna wanna do this again.
Oh, yeah.
So if I clean up the first term, what do I get?
8x cubed.
Good, okay, we combine the constants, we get 8x cubed times plus second term.
3x. And you just
Okay.
figure out a bunch of stuff.
Good, yeah, now we're looking for greatest common factor, right? And there's, you're always just gonna look for, is there a constant? Well, no, there is no common factor of 8 and 3, is there?
No.
Right?
No.
But then we look at the like bases, right? And so, look, we've got, here's one base, we've got x's, and then we have another base, 2x minus 9. Now I got what Easter colors from Kindle, I'm not sure what I did on that. But, okay, so we can factor out the greatest common factor, meaning the smallest power of each, right? The smallest one that appears to be the greatest common factor. So, 8. What's the biggest common power of x? X squared. This one can give away x cubed, but that one's only got an x squared to give, right? So
X.
x squared. What about the 2x minus 9? What's the greatest common power of
3.
3?
Wait, why wouldn't you
Whoa.
just what was that?
Why'd you take the 8?
Oh, sorry, can't take
Thank
the 8.
you.
Sorry, I don't know what I was doing.
Okay.
I don't know what I was doing with that. Sorry. That was
I
my
had no
mistake.
idea what was
I
going
see.
on.
I thought there was no factor we could
Yeah.
take from the constants.
You're right. Okay, so there we go. Good.
Yep. Now we're good.
Okay, and now what's left over when we do that?
8x.
Yes.
Okay, so we get 8, and then I cancel all but one of those, right? So I get an x, and those went away completely. I factored that out completely. Plus
3.
3,
2x minus
took
9.
that all the way out. Took all but one of those, right? And then sometimes it got left there too. And that's, that was pretty good, but there's, now all the 99% of the hard work's done now. All you gotta do is just distribute the 3 and add up like terms, right? Yeah. Okay, so,
Yeah, that's exactly what I forgot to do.
and so what do we get then? We distribute the 3 and add up like terms. Good. 14x minus 27, and that's it. Now we got it completely factored. Yes, ma'am.
When we put it in, do we have to put the first term segment thing, like the x squared plus, or times?
Does it have to be in that order?
Well, do we have to keep that in there, like always?
Which, keep what in where, I guess.
Okay, farthest left hand,
Okay, right here?
yeah,
Mhm.
like that crap right there.
Mhm, okay.
And then when I'm putting in, like, the answer,
Uh-huh.
I gotta keep that.
Meaning it needs to be factored. Yeah, it should be.
Oh,
And that's, and once again.
Wait,
Yeah.
So you do put in the x squared and 2x
Yes,
minus
yes.
9
You have to
That
put
was
that.
where I.
quantity cubed?
Yeah,
Okay.
yeah. And that's, you know, that still is probably a little bit of a mystery to you guys. Why would we want these things? You know, why is that better than, say, that?
Yeah.
I'm sure that still is a little bit of a mystery, but here's, for now, it's gonna become abundantly clear to you very soon when we get into chapter 3 and we start actually doing the analysis that is meant to go with the calculus, that that's a big deal. Typically what we wanna do, remember, is we wanna find the zeros of the derivative. And to find the zeros of the derivative, it has to be factored, because then we can use the zero product property, right? Remember, that's how we solve complicated algebraic equations, is we try to factor them and then set each individual small factor equal to 0 to find the zeros. So factoring is something that's always gonna be our goal. And we're just working on, really, these are just kind of the skills that are gonna take us into the really heavy differentiation stuff, which is next chapter. Okay. Not that it's heavy, meaning it's real hard, it's just, it's the application of optimization. That's what we use differentiation for mainly. That's what we're gonna do next chapter.
Sounds fair.
Okay? All right, moving on. Okay, this one isn't a big deal, but let's just at least take a look at the wording of the question.
Let's do it anyway.
Can I do?
Oh, this is the double
Oh, that's probably a little better.
Mhm. Yeah, I like these.
The double rib. Is this the one that we were saying right
No. This is that.
Oh, yeah,
This is double derivative.
Yeah.
So acceleration.
Yeah.
Okay, so,
Yeah.
so what we got here, this is
So yeah.
just a little calculus problem, just disguised in a kinematics problem. But all it really is, you just gotta remember, the relationship here, the physics relationship, is just that velocity relative to position is derivative of position with
Yeah.
respect to time,
Yeah.
right? So it's just s dot. And acceleration is,
Double derivative.
v dot or s double dot, okay? Second derivative of
Wait, can you say
position.
that one more time? What was that?
So yeah, I'll write it down. So v equals ds dt, or s dot. A equals dv dt, or v dot, which is s double dot, second derivative.
Okay.
And so we're given s. How do we want to write that though in order to do a derivative?
1/2.
1/2 power. Okay, and so it's just a matter of doing the derivative twice. Now it is going to get a little bit uglier when you take the second derivative. Let's go through this one. So v then equals s dot. What is this chain rule, right? Outermost layer is 1/2. Good. So we got hand to the 1/2. So we get 1/2 hand to the negative 1/2. What's hand? Well, 92 plus 4t. So what's the second length in the derivative of the inside layer? 4.
Which then equals 1/5.
Yeah, good. 4 times 1/2 is just 2.
Yep.
Good. And so we end up with v equals 2 times the quantity 92 plus 4t to the minus 1/2. And they want us, okay, we'll just leave that there for a second. We'll come back to that. What about acceleration then?
Take derivative of that.
Yeah, derivative of that. So A is gonna be, just leave the 2 out front.
Yeah.
And everybody's okay with that, right? Because the 2 is just a constant, so we'll just leave that out there and differentiate the function. So 2 times, what's the derivative of this part then?
Negative 1/2.
Yeah,
And-
hand to the minus 1/2, so negative 1/2. Hand to the, what? Say it again? Negative 3/2, yeah. Because we're gonna subtract 1 from
Lunch.
negative 1/2, right?
Oh.
And then once again, the derivative of the inside, 4. Good, so, let's see, we get if we combine all the constants, I guess I just get -4, right? Because 2 times -1/2 is -1 times 4. -4 times quantity 92 plus 4t to the -3/2. And now all they ask us to do
Plug it in.
is just evaluate. Yeah, we'll just plug in 2 for t, okay? And 2 for t, that sounds very British. And so v of 2 would equal what? If I plug in 2, what's the argument, this number inside gonna be? 100, yeah, the square root of 100.
10.
But if it's the negative square root, what's that mean? I mean, if it's a -1/2 power, so it's on the bottom. Yeah, good, so we get 2 over the square root of 100 just equals 2/10 or 1/5.
Oh, ho, ho, ho.
Or 0.2, yeah. However you want to slice it there.
Oh,
Never be
why is that so much easier?
Okay, and if I plug in 2 down here, I get -4 over 100 to the three halves. Negative just takes it to the bottom. Yes, ma'am.
For acceleration, how do you get S double dot? Like, how do you know that?
Okay, just because it's like velocity is to position as acceleration is to velocity. So you're just, but when you differentiate velocity, all we're doing is we're taking the velocity function and differentiating that. And so that would be, think what we've done to the position then. We differentiated once to get there, we differentiated twice to get there. So that's what the double dot means, just a second derivative. Does that make sense?
Kind of.
Okay, what?
Like,
Are you
how
sure?
do you, like, why is, so acceleration equals to velocity?
Yeah,
Okay.
so here's the rule. So velocity is the derivative of s with respect to t, right? Acceleration is the derivative of velocity with respect to t. But velocity, really, if that's already just the first derivative of position,
Oh, I
that
got
makes it a
it.
second derivative. Okay, good, all right. And so then, now how do, remind me again, what does 100 to the 3/2 mean? How do we?
Square root cube?
Good, exactly. It's the square root cubed. Square root of 100 is 10, cubed is 1,000, right? So we get -4 over 1,000, so that's -1 over 250, right? Makes sense, or -0.004.
So you take the square root first and then you times it by?
Yeah,
Yep.
times
Then you
that.
cube
Then you
it?
cube it, yeah.
Okay.
Or we can just plug it into your calculator.
Fair enough.
Yeah, that works for me, yep. I like that.
Okay, questions on that? We good?
I was thinking we could do better.
I think you are too. You're getting this stuff.
I still don't know.
Okay.
What is
so,
that?
Yeah, okay, here's another one.
Oh,
Tons of questions
I
on
can do
this.
this one.
Yes.
This one.
I'm pretty sure I can do this.
I spent
Okay.
almost a whole entire class looking at this.
Pretty sure I
They
can
have
do
one
this.
after this.
Okay.
This is my first question on the test.
This is a little tricky, I agree.
Kinda get a bit intimidated.
Okay, this is kind of a different
Kinda like that.
way to represent the chain rule.
Oh.
The way to think about this one
Go
is
off on it, we're all-
not like you're differentiating the layers of an onion so much, because it's not such an obvious, function of a function. But we're gonna use the ratio form of the chain rule, because look what we've got here. We've got x's and y's written in terms of a common parameter, t. This is a system of parametric equations, is really how we describe that,
I got
okay?
this one right.
Yeah, I'm still-
So we're able to do this, we're able to say the derivative of y with respect to x, remember, is equal to the derivative of y with respect to t times dt over dx, right?
Yep.
Okay, now I think an easier way to think about that though if you like that, you take your pick, whichever way conceptually, meshes with the way you think about this is fine. But another way to do that would be to just write that as this ratio, so dy, this is how I would always do it personally, but that's just my own personal bias. Dy dt divided by dx dt,
Yeah.
okay? Doesn't that, to me, that just seems a little bit easier to think, but no, I've seen some people shaking their heads, people don't like it that way. True, I mean, I get that. Now think though that really what look like fractions there may not necessarily be fractions. These just mean derivatives,
I
right?
like that better.
Okay? So if let's just take these two functions and let's just find dx dt and dy dt, and then we can use either way we want to, it doesn't matter. So if x is 5t,
This would be 5.
oops,
Oh, 5.
if x equals 5t, dx dt is what? 5. Okay? If y equals square root of t, we'll write that as t to the 1/2, then dy dt is what? Good, 1/2 t to the minus 1/2, right? Which is the same thing, minus 1/2, which is the same thing as 1/2 times t to the 1/2, 2 times the square root of t, right? Now, is everybody 100% comfortable with that?
Absolutely, I am.
Okay. Any questions at all on that?
No, sir.
Okay? So all we're doing then is taking these two functions and plugging them in there and there, or there and the reciprocal there, right? If dx dt is 5, then dt dx is just 1/5, right? It's just the reciprocal of dx dt, okay?
Absolutely.
So either way, I'm gonna go ahead and use this one, but however you wanna do it. So dy dt we said was 1/2 times the square root of t divided by 5. And then really we end up doing this anyway, don't we? We're just gonna flip and multiply by the bottom, right? So that's equal to top fraction times the reciprocal of the bottom fraction, right? And that's just our, we've done that for years and years. If we're doing algebra involving rational functions or fractions on the top and fractions on the bottom, we'll just flip and multiply by the bottom. And we end up with, it looks like, and are we supposed to evaluate this maybe or something too? Yeah, we're supposed to evaluate, find a tangent line, okay? So, we didn't even have to simplify this thing, did we? I mean, this is unnecessary. Once we get the derivative written like this, let's just plug in 1/4 and, we don't need to turn this into a nice, neat, simplified function. So let's not. That's just borrowing trouble. Oops, not too far. There we go. Okay, so then, f prime of 1/4 just equals 1/2 times the square root of 1/4 divided by 5. And what is the square root of 1/4? 1/2 times 2. So that's just good. So we get 1/1. Yeah. Everybody see that? This whole thing right here is just going to simplify into 1.
Oh.
Right?
And you plug in 1/4 for the x and the y, and then you get your tangent line.
Yeah, good, good. And so then to get the value, so there's our slope, right? This is the slope of the tangent line.
Other one.
Say it again.
Oh, never mind. Sorry. I found it.
Okay, all right. So there's the slope of the tangent line. To come up with the equation of a line, right, we just need a slope and a point. So all we need now is to know the values of x and y at t equals 1/4. Well, that's easy. Just substitute 1/4, right? That's the value of t. So we get up here, x is going to be what then? 5 times 1/4 is 5/4, right? And y equals the square root of 1/4 equals 1/2, right? And so we get this slope, and we get the point 5/4, 1/2. Okay? And now it's just a matter of doing some, some really algebra 1, maybe a little more complicated, 'cause we got fractions, but for you guys, it's nothing now. So we'll just say,
Gosh, I hate fractions.
remember how we do this? And I know a lot of you guys probably learned how to do this doing point slope, but this is really easier, just to plug in M, plug in a solution to solve for B, right? We just need to know the values of M and B, and then we got our line. So we got M. If we plug in 1/2 for Y, X is what, 5/4? So what's B gonna be? Let's see, the 5's cancel, so 1/2 minus 1/4 would be 1/4. Everybody agree? Okay, got B, got M, so our equation is Y equals 1/5 X plus 1/4.
Now, where'd you get those points again?
Where to get the points? Points are because I know X equals 5t and Y equals the square root of t, but we're looking for the equation of the tangent line defined when t is 1/4. So if t is 1/4, I'll just plug that value in for X and Y to find out what the values are.
Gotcha.
Okay?
There you go. Okay.
Yes. Okay, make sense? Okay. All right, moving on.
I like these.
Yeah, this one would, you tell me, I'll make it bigger, you tell me if you wanna do this or not. This is one that I think for the most part was pretty good.
do it.
This one is not going out, it's like Anthony, you were so pretty proud of yourself.
Okay,
Just so I
yay
know
or
what the
nay?
answer was.
Thumbs up, thumbs down, I don't care. Thumbs up meaning,
Yes, do it.
meaning, you wanna look at it? Anybody wanna look at it?
No.
Okay.
That's good.
We might as well just like.
Do it.
Because they need to.
Okay, take a quick look, take a quick look.
Yeah.
All right, so if we differentiate,
During the time.
first one we get,
You're fine.
There's nothing wrong
Okay,
with
good,
that,
so
I just wanna look at it.
we get product rule, right? So, if I do first times derivative of the second, I get 5x squared y prime plus 10x y. Everybody okay with that?
Yeah,
And once again, because
I am.
derivative of y is y prime, but the derivative of x squared is just 2x, because we're differentiating with respect to x,
Yeah.
right?
Mhm.
Okay. Plus, what about over here? Well, I've got a 2x times the derivative of y squared would be what?
Y prime.
Good, 2y y prime plus y squared times the derivative of 2x, 2. Equals derivative of -5, 0. Good, so then, if we clean this up, we get 5x squared y prime plus 10xy plus 4xy y prime plus 2y squared.
Bless you.
Okay?
Thank you.
Get the ones that aren't white.
Yes, we'll push all the non-y prime terms to the right side and factor out a y prime on the left. Okay, let's just do those two steps in one. How about, so that gives us y prime times something equals, we're gonna pull the 10xy term and the 2y squared term over here by subtracting them.
That's correct.
And then that leaves us with just those two, so we'll factor out the y primes. We get 5x squared plus 4xy. Good, plus 4xy. Just divide, so I got divide both sides by this leftover factor. And we got it, yeah, that's y prime.
Change it to y squared.
Okay.
Okay, and were we supposed to do anything with that, or just take the derivative? Yeah, just take the derivative.
That's it.
So we got it. Okay. Good? Whoops.
God, it's sweaty.
I think we're good.
Oh, God.
Well, x equals cosecant y.
Yeah, let's do it.
Okay.
I don't know, I have no idea.
Let's do it.
I have no idea what that is.
I didn't get this problem. Oh, yeah. Oh, yeah. I realize that.
Or x not equals y.
Yeah, I realize that.
Okay, so
Oh, damn.
if we differentiate this, then on the left side, we just get 1. On the right side, derivative of cosecant y with respect to x. What's the outer layer there?
Cosecant of hand.
Yeah. The derivative of a cosecant is good. Negative cosecant
Tangent y.
cotangent y, and then the derivative of what's inside is. All right, good. So, okay, so then, okay, how do you deal with this? Suggestions.
Divide.
Okay, we can do that. We can divide both sides by cosecant y and cotangent y.
Then once you split them up.
Then, okay, it's probably not a bad idea here. If we really want to simplify this, cosecants and cotangents are kind of
So make them
They're
into a
neat.
fraction.
good. We want to make them into, we want to write them in
Yeah.
terms of the elementary trig functions, in terms of sine and cosine. And we might as well do that now, really. What is cosecant? C goes with S, right, and S goes with C. Cosecant is the reciprocal of sine. So we end up with 1 equals negative 1 over sine y times
Cosine y.
good. So that just makes, really, then this just becomes a sine squared.
Yeah.
And that's really just a minus cosine y on top, isn't it?
That would be correct.
Right. Times
Right.
y prime. So we'll just multiply both sides by the reciprocal, right?
Mhm.
And so y prime just equals negative sine squared y over cosine y. Just pull the negative out front. Okay, make sense?
That's it.
Is that good?
Okay, so wait. So
Back
negative
ten working
cosine
down,
y.
you could get
You're fine. I kept thinking it. I wasn't sure what it was.
That's okay.
So if you wanted to, you can switch it back to the code. No.
Yeah, but you really wouldn't,
Yeah.
it'd make it more complicated.
Yeah.
You'd really rather just leave it in terms of the sines and
Yeah.
cosines.
Yeah.
Okay. And you, I mean, you could do,
Right now.
theoretically, there's one more thing you can do, but it doesn't buy you anything, so it's not worth it.
It's so nice.
I know it's an hour ahead.
Okay, this one, gosh, I wish we would've done this one instead.
What's this?
This is with
Let's do it
tangent
tomorrow.
normal.
Do it tomorrow.
Do it tomorrow.
Yeah, okay, I'll tell you what we'll do. I'm gonna, just, let's go ahead and say, because I do want to go through a couple related rates ones too. I mean, these related rate stuff, I'm sure you've started, they can be tricky, and there's a lot of little intricacies on those. I think one of the ones that we, looking back and kind of thinking about what we did and looking at the test, I don't think maybe we did enough angle. I don't think we looked at enough
okay. I didn't
angle
know how to do
examples.
that
So
one.
let's look for sure at a hard angle example,
It's like that building.
like the building one, or I'll pick one sort of like that one. Yeah.
What about the
Yeah.
what about the ones that
Oh,
are
yeah.
like y6 cosine pi x minus
The
y?
pie ones, the pie ones.
Okay,
I
the
can
pi
do the
ones,
pi.
wanna look at the
I
pi
can
ones?
do
the
like
pi.
pi and then it's got like cosine of pi.
Okay.
I can do
Yeah.
that.
Okay, so we'll finish this up and hit one of those and one of, yeah.
Started my career.
I was just thinking, oh my god.
Eric Davis, please call extension 304.
Who's one of the Heisman's here? Yeah.
That's a slam dunk, isn't
Oh
it?
yeah, it's not even fair. Jameis Winston's gonna win it. Just kidding.
He's not even in the mix.
No. I think that
They released the official, what's
yeah,
that?
They did the final six last night.
Yeah.
I think the guy from Boston College should have a chance.
Yeah,
2,000 yard rusher. Since 2007. That's
Yeah.
impressive.
playing for Boston College.
Yeah.
Yeah, but what cornerback plays without his contacts in and has his,
So I mean,
team
what is he? 6'5"?
6'5", redshirt
He's a
freshman.
man.
Yeah.
Redshirt freshman, doesn't play with contacts in.
Yeah.
I mean, how are you not gonna win the Heisman like that?